hit a couple little things from circular functions that I don't think that I expanded on quite enough. Did y'all do 25 through 36 on page 340? 340, 25 through 36, where you had to use this unit circle to answer? Okay. So I'm going to hit a little bit of circular functions, and then we're going to move into sine and cosine graphs and tangent. Are you done? All right. Let's see. If I have the point P that is 3, 4, and this is on the terminal side, how might I write all of the trig functions based on this? Let me just draw it for you. Here's P, right? I'm in a standard position, so this is my, but how might I write, here's theta. How might I write the sine, the cosine, and the tangent of theta from this point? This point is 3, 4. What would the sine of theta be? Okay, that's if you're on the unit circle, yes, because the hypotenuse is 1 on the unit circle, but I'm not on the unit circle right now. Does everybody see what I'm saying? If I were on the unit circle, that's a pretty good circle. If I were on the unit circle and I'm at this point, the coordinates here would be, let's say, square root of 2 over 2, square root of 2 over 2, right? Thank you. Yes, in this case, the cosine of theta would be the square root of 2 over 2. But the reason that it's the square root of 2 over 2, if you think back and remember this triangle that we drew, it's opposite. So this length divided by hypotenuse, and the hypotenuse was 1, right? Are y'all following me? It's exactly SOHCAHTOA, but with points. But what I have to do is I have to think about it in terms of this triangle. So if this point is on my terminal side of my angle, okay? So a standard position, here's my initial side, my theta is measuring this way. If I drop this down and made a triangle out of it, what is the height of that triangle? What is the length of that triangle? How could you find the hypotenuse length? Pythagorean theorem, right? So 3 squared plus 4 squared equals whatever that hypotenuse is squared, right? The reason the unit circle is so much easier to do this on is because the radius is 1, so every hypotenuse is always 1. And if you divide anything by 1, you still get itself. Here I'm not dividing by 1, so it's not just the y-coordinate, it's the y-coordinate divided by the hypotenuse. Does that make sense? A little bit? So this is 9 plus 16, 25. This, in fact, is a 3, 4, 5 triangle. Now can you find all the trig functions of theta? Okay? What is the sine of theta? 4/5. Opposite over hypotenuse. What's the cosine of theta? That's right. How about the tangent of theta? Cosecant? Secant. Cotangent. I really want you to make the connection between the unit circle and this and why they're different, and we're still doing the same thing. It's just my hypotenuse length that has changed here. Does that make sense? No, it's always applicable. It's just that its radius is 1, which means the hypotenuse of the triangles that I'm finding are. It's applicable to all the trig functions which we are doing today, which you are going to find. Because 3/4 is not on the unit circle. Correct. Obviously, you can't use the unit circle for something that's not on the unit circle. Yeah, I wouldn't say limited. I mean, everything's limited in its own capacity. Now, that's a whole other, you're not comparing apples to apples. Yes or no? What if I move the point? What if I said that this point was, oh, I don't know, -1, -1? Same process, but find all values of theta. Find all trig functions of theta. And remember, your standard position, your terminal side is the x-axis. It doesn't matter that it's on the negative side of the x-axis as long as it's still the x-axis. Do you see theta? I'm still measuring initial, terminal. Yes, dear. Your initial side, it's always the axis. It's so if I'm in quadrant 3 here, then it would be the negative side of the. I want to use it to set up my triangle, my reference triangle, and so to do that, I couldn't have a right triangle the other way. I would just keep it in radical form. So this length would just be square root of 2. You don't have to worry about negatives because length can't be negative, right? As you go through and do that. But can your sine and cosine and tangent be negative? Sure. We know that from the unit circle, right? I did. Mm-hmm. All right. What is the cosine? If I rationalized it. Oh, this is interesting. How about the sine? Same thing. Tangent. And then, of course, we're flipping for the cofunctions. So secant would be negative square root of 2. Cosecant, you don't negative reciprocal, you just reciprocal. I flip the non-rationalized because then it would put it up top. If I flip the rationalized, I'd be back on the bottom and then I'd be doing more work. Yeah, either one. Either one. They're equivalent fractions, so either one. If I'm at the point if I'm in an interval, not at a point, so now I'm thinking back to the unit circle. If I am between the values 3 pi over 2 and 2 pi, where am I at on the unit circle? Where? Brett, where am I? How do I even, where is that on the, this is why. No, it's not a point. I'm not talking about a point. I'm talking about x being between, if x is on the interval 3 pi over 2 to 2 pi. Quadrant 4. Do we all agree? 3 pi over 2 is the bottom of my circle, and then around to 2 pi. So I'm in quadrant 4. All right, if x is between 3 pi over 2 and 2 pi, right? Or I should say my theta values. If my theta values are between 3 pi over 2 and 2 pi, I'm talking about these values. I'm talking about quadrant 4 on my unit circle. So the directions are if t, so we'll call this t, is in the given interval, then what is the sine of t, the cosine of t, and the tangent of t sine-wise? In other words, is it positive or negative in that interval? So when I'm between 3 pi over 2 and 2 pi, is the sine positive or negative? Why? The y is negative. I'm in the bottom. Remember, this is where x is positive, y is negative, so tangent would also be negative. So the sine, which is the y, is negative. The cosine is positive, and the tangent, we said, was negative. That's the way it'll be in your homework. They use the variable t. Okay, so I'm just thinking about this unit circle, and I'm thinking about being down here. And down here, remember, I'm positive, negative. My x is positive, my y is negative. And if I divide the two, of course, I will get a negative. Mm-hmm. This just means negative. This means positive, and this means negative. So because I'm in this quadrant, because this is 3 pi over 2, And if I loop back around, this is 2 pi. So I'm only in this quarter of the circle. Because x is always positive in this quadrant, and y is always negative. So this is my x, and this is my y. And remember, this is y divided by x. I'm almost done with this part before we graph sine and cosine. I know, Brett. If theta, and this is just really some applications of unit circle to make sure you understand how to use it. If theta is 7 pi over 6, what point would be on the terminal side of my angle? If theta is 7 pi over 6, what point would be on the terminal side where it ends on right? Good job. All right. So my theta is 7 pi over 6, right? What point would be on the terminal side? Not being on, but remember I started the x-axis and then I loop around. So yeah, what's the point there? Negative square root of 3 over 2, negative 1/2. Where is 7 pi over 6 on here? It could be radians too. So the directions for this say, choose the point that is on the terminal side of theta. So we're just looking for, what if it was 45 degrees? What point would be on the terminal side? Right. Go on your unit circle. Go to that point on your unit circle. Okay. When we did must-know functions at the beginning, sine and cosine and tangent were on there, remember? We're going to talk about them just in a little more depth. That's why we're not going to spend a whole long time introducing them, but now we're going to see why, using our unit circle, these values are what they are, okay? So if you think back, I guess this will be graphs. Remember we had sine x. Remember what that looked like? What it looked like? Wavy lines. It's a wave. It's a wave graph. That's exactly right. So I told you when we were doing it not to worry so much about the units that we were putting on here because they would make more sense a little bit later on, and I hope now that they make a little more sense than what they did before. What is the biggest value that sine, just plain old sine, ever takes on? Why? It does oscillate between -1 and 1. Why? Look at your unit circle, because it always comes back to the unit circle. The highest I ever go, because height is my y, right, and that's my sine, is 1, and the lowest I ever go is -1. The radius is 1. That's exactly right. Well, we're going to talk about that. I'm glad you asked. It absolutely would. We're going to talk about transformations of these trig functions. You're just ahead of the game, Brett. So impressed. Okay, so on here, to make this a little easier to graph, what we do, what? We pick points that are going to be easy for us to graph. And looking at your unit circle, the places that are the easiest to graph are the places where it is either 0 or 1. Okay, and that's why we go by half pies, because each click is a half a pie, right? All the way to the top, all the way to the side, all the way to the bottom, and around. So that's why I go by half pi. So I've got pi over 2, pi, 3 pi over 2, and so on, and I can go negative. Do what? It is. Because I can keep looping around. Right. Kind of. So if this is the graph of y equals sine x, I'm putting in values for x, right? So I'm looking at the sine of pi over 2, the sine of pi, the sine of 3 pi over 2, and I could keep going around that circle to find more values for sine. All right, so as you try to figure this out, I always, when I'm trying to figure out what's the difference in sine and cosine, I'll close my eyes and think if I'm at the top of the circle at 0, then what is the sine value there? 1. And then, oh, not at the top. The top is pi over 2. That's 1. At 0, what is the sine? 0. So I start at 0. At half a pi, my y is 1. At a whole pi, what is my y? 0. And then it's easy just to pick up on the pattern, right? This is, yes. But I really hope you see why these values are what they are now. Everything's important. So, of course, my domain is all real numbers. My range is what? -1 to 1 inclusive. How does this compare to the graph of cosine? It's just shifted. You're exactly right. So the cosine of 0 is 1, brackets. How about the cosine of pi over 2? And then I can pick up the pattern from here. So plot it against each other. Looks kind of like this. We're going to stick just with sine and cosine today. We'll talk about tangent some tomorrow. Tangent is its own, it's a little bit more difficult. But as we talk about transformations, we're going to stick just with sine and cosine today. But just a little bit of terminology that you may or may not have heard of before that you may or may not remember. Amplitude. Every sinusoidal graph has an sinusoidal the graph of a sinusoid, which is any cosine or sine, cosecant or secant graph. But the sine and the cosine graphs have amplitude and their cofunctions. Does anybody know what amplitude is? The amplitude is often referred to in layman's terms the height of the graph, okay? It is the max minus the min divided by 2. It is always positive. And so on the parent graph, what would the amplitude be of sine or cosine? It's 1. Highest it goes is 1. The lowest it goes is -1. 1 minus -1 is 2, and 2 divided by 2 is, it's half this distance because that's the lowest it goes. So it's 1, okay? If the x-axis cuts it exactly in half, then it's how high up it goes. That's why I said height, put in quotation marks. Y'all okay there? Okay, good. The other thing is the period. What is the period? What does that mean? Have y'all not hit on this in any other class? Normally you will have hit on it in like, how frequent the pattern repeats itself. So in other words, how long it takes it to do an entire loop, an entire cycle, we'll say. And this is not very mathematically correct terminology here that I'm using to define these, but just so that you understand. So if I look at the graph of sine or cosine, what is the period of those sine graphs? It's always the same on a parent function. How long does it take it to make one complete cycle before it starts repeating? What is it? 2 pi. 2 pi. It's always 2 pi for the parent graph. We'll talk about frequency as well, which ties in with period, but more just how to find it than what it does for right now. All right, let me talk about transformations, and then I'll be done. Is everybody okay? Am I throwing too much at you? Too quick? Yes. I'm going to show you how to do that. Based on, I know, I'm sorry. There's an easy way to do it if you're given the equation. On some of them, yes. I should call this transformations. While a lot of things hold true, a lot of things are different. I have a lot of variables in here. This could be sine, cosine, tangent, cosecant, secant, or cotangent. This would work for all 6 of your basic trig functions, yes. No. Maybe. It shouldn't take up too much. Let's just focus on sine and cosine for these right now, instead of focusing on the others, because I'm going to give you some specific things that this does for sine and cosine. All right, so the A in front, remember that has always been my what? That's exactly right, my vertical shrink or stretch. And while it still is, and it still does that, what it also does here is it tells me my amplitude. And in fact, the absolute value of A tells me the amplitude of the graph. So if you think about that parent function, y equals cosine x, what is the A in that equation? 1. So it makes sense there that the amplitude is 1, right? Is everybody okay on that? The period is 2 pi divided by the absolute value of b. Okay, so what was my b in the parent function? 1. So what was the period? Frequency is the reciprocal of period. Okay, so to find it, I'm just going to flip the period over, and it will tell me the frequency of the graph. Let's see. All of the other, my stuff still stays the same. This is still vertical shrink or stretch. Horizontal shrink or stretch. But notice how it's factored out. Do you see that? How it's in parentheses there? If I had the sign of 2x plus 6, my c is not 6 there. It's 3. I would have to write it as the sign of 2 times x plus 3 to find b. So be very careful and make sure, in fact, I'll put a note, make sure to factor out b. Otherwise, your shift's not going to be right. Yeah. Because, okay, it has to be written like this. The value in front of x, the coefficient in front of x, has to be factored out from the value that follows x. Okay? If it's not already written like that, so in this example it wasn't written like that, I had to factor it out. Even if it doesn't factor out nicely, you have to factor it out. If it was the sine of 3x minus 1, I still have to factor it out. It's still got to come out, so I would have to do sine of 3. What would be left on that 1? 1/3. So it still has to be factored out regardless. Does that make sense to you? Okay. That, of course, still gives me my horizontal shift, which we will also call now a phase shift. You see that terminology? And what's the D do? Up or down. That's exactly right. Still the same thing. Vertical shift. So I know this looks like a lot, and it is. But it still should be stuff that you can do. We'll do a couple examples. Remember to go off of your parent graph there that we found in the beginning. Y'all got that? Let me wait a minute. Are y'all sad today? What's wrong? We will be graphing them by hand, yes. Some of them, yes. I'm gonna show you. I'm gonna do a couple examples. All right. Some of it you can, some of it you can't. Most of tonight's homework is non-calculated. I know. All right, let's do some examples. I'll be working problems from your homework. Number 3. Find the amplitude of the function and use the language of transformations to describe how the graph of the function is related to the graph of y equals sine x. Okay, so 2 parts. 1, amplitude. 2, what's the transformation is basically what they're saying from the parent graph. Not graphing just yet, no. So what's the amplitude here? 4. It's just got to be positive. Now, does that make sense to you when you know what transformation this is? What's the transformation here? It's a vertical stretch. You're right about the reflection, but hold on, we'll get there. It's a vertical stretch of 4, right? Which means every x stays the same, but every y gets multiplied by 4. So if I'm thinking about on my parent graph, and I start here, this is the point 0, 1, right? Here's my little wave. This point now becomes what? 0, 4. And the one down here becomes whatever this point is, right? Pi over 2 pi. Unless I transform it, the parent. But I've multiplied everything by -4, right? Now I haven't flipped it yet, and I can go back and flip it, but just to show you how amplitude relates to vertical stretches and shrinks. But we do also, what am I reflected over? Do you see the connection there with the amplitude and the stretches, shrinks? What were you fixing to ask, Kirsten? Stretch it first, then reflect it. All right. How about number 11? Yes. A lot of this is going to be looking. You won't have a whole lot of graphing, but what's the period here? What is it? How'd you find it? 2 is my B, right? Here's my A and my B. So to find period, I do 2 pi over the absolute value of B. What does that mean? I saw you do that. But you're right. It means it's shrinking it in, right? It means instead of taking 2 pi to make a whole cycle, it's doing an entire cycle in just pi. So instead of it taking out to 2 pi and going, and I'm at cosine, so I'm starting here. Instead of doing this, it's now doing this. You see the difference? So this would also be considered what in transformation world? Horizontal shrink of 1/2, right? Did you see why? Shrunk it in horizontal. You see the connection here? Is everybody okay? But is there any way to say that without it, like figuring it out? You're just going to say, you don't have to do the graph. I was just using that as an example. This is what you would say. It asks for the period, and then it asks for the transformation. So the transformation is a horizontal shrink of 1/2. It's the flip. Remember, horizontal is always opposite everything. But this one also has a what? A vertical stretch of 30. It flips. It always flips. Horizontal is always opposite. If you're subtracting, you're moving right. You're doing the opposite. If you're doing a stretch or a shrink, it's the flip of it. The 2 is the B. That's right. You have to factor it out if you have a C there. Yes. Only if you have a C. You flip that B over because it's horizontal. What's the vertical stretch impacting? The what? The amplitude. It impacts the amplitude, which is the A in front. What is the amplitude here? 3. Let's do number 17 together. Now we're going to graph. The directions say to graph one period of the function. Use your understanding of transformations, not your grapher. Be sure to show the scale on both. So what I'm going to do is I'm just going to start here with my parent graph. Always have the same units. This is a given acceptable units of a trig function graph are half pies. They are as standard as a single unit on a regular graph. And you don't have to graph the parent. I just want to show you plotted against each other what happens here. And it said one period only. So first of all, before I graph, what is the amplitude of my graph? 2, which means what? Vertical stretch of 2. And because I don't have any shifts up or down or left or right, but specifically up or down, that means my maximum is going to be 2 and my minimum is going to be -2. Okay? How do I take these points? Because there's no shifts or anything. How do I take these points with a vertical stretch of 2? Multiply the y by 2. And it says just one period, so I'm just going to include this portion because that's one period, right, out to 2 pi. If I calculate the period, remember period is 2 pi over b. So the period here is just 2 pi. So I'm going to go from 0 to 2 pi. Y'all okay there? This point becomes what? Y'all can do this. Pi over 2. Only do the y since it's a vertical stretch. So pi over 2 stays pi over 2, but the y becomes 2. Remember, it's vertically stretching. My x is staying the same, but I'm stretching it out this way. 0, how about this point? -2. And then, of course, the 0. So this would look like that in just one period. I am going to stop there because I don't want to throw too much on you.